Welcome again, everyone, and thank you for joining us on today's webinar, Best Practices for Solving Crude and Fuel Blending Challenges. I'm Allison Sterling, Director of Marketing at Emerson, and I'm pleased to welcome you to our Emerson Flow Expert webinar series. Before we begin today, I'd just like to take a couple moments to acquaint you with your webinar environment. I wanted to give a first kind of comment that we do recommend that you not use Internet Explorer as it doesn't properly render the slides. We recommend that you use Firefox or Chrome. So if you are using Internet Explorer, it might be beneficial to change over, or you can wait and see if you have an issue. As you look at your console that you're logged into, you will see a presentation window on the left side, a Q&A chat window in the upper right-hand corner, media player controls, and a resource box with related content that you can view and download during the event. You can resize, move, or minimize any of these windows during the event to fit your viewing preferences. At the bottom of your display, you'll see a row of icons that also give you some added capabilities, where you can share the webinar via social media channels or request a visit from our Flow experts. Throughout our webinar today, we encourage you to interact with our speakers by typing in questions and comments using that chat panel. We will be answering questions at the end of the webinar. We're also recording today's session, and we will make the link to this recording available 24 hours post-event via email. On today's webinar, we are lucky enough to have joining us Julie Valentine and Arnie Josephson. Julie Valentine has been with Emerson as a refining industry marketing manager for over 20 years. Julie is a graduate of the Colorado School of Mines and has authored numerous technical papers on various applications of flow technology in the refining industry and is a co-inventor in 2 U.S. patents for micromotion. Arnie Josephson has been involved in the industry since 1967 in a variety of roles, including research and development, engineering, planning, operations, and consulting. During the past 20 years, he has built upon his blending experience by consulting and managing projects in fuels, lubricants, and greases. Arnie now serves as a business development manager and a subject matter expert in blending and transfer applications for Emerson's flow systems and solutions. Welcome, Julie and Arnie, and I'll hand it over to Julie.
Thanks, Allison, and welcome to the webinar on blending in refineries. We hope that you find it to be informative and helpful. So in this webinar, we will be discussing blending at both ends of the refinery to include both crude blending, but also fuels or product blending. We will first talk about the challenges that are associated with processing and blending of opportunity crudes, and also the current challenges meeting product blending requirements. Emerson has added to its blending portfolio and experience with the acquisition of a company with over 50 years of experience designing blending operations and providing integrated blending solutions. We'll talk about Emerson's technology solutions for blending and also the services that are available to economically evaluate, design, execute, commission, and support a project. We will then discuss several case studies providing proven results, followed by the answering of questions you've submitted in the chat section, as Allison just described. So first, let's talk about the challenges. So blending of crudes and fuels isn't getting any easier with the current market dynamics. The processing of opportunity crudes, including heavier, lighter, higher acidity, more paraffinic types, etc., has led to significant challenges in the industry. Accurate crude characterization is extremely beneficial in order to process crude most effectively. With the processing of certain opportunity crudes also comes the risk of corrosion, fouling, and catalyst poisoning, which limits the optimal quantity to be processed. On the fuels blending side, there are a number of new complexities as well. There are an increasing number of environmental regulatory requirements to produce clean fuels and reduce vehicle emissions, which results in new and tighter product specifications that we have to meet. The blend components also have increased variability with the processing of varying crude slates, and some refiners are also blending in biofuels or blending stocks that will add biofuels at the terminal. So how do these changes then make the day-to-day operational challenges more difficult? Well, tank storage capacity limitations and inventory costs seem to be an issue for almost every refinery. Anything you can do to utilize your existing storage capacity in lieu of adding additional tanks will always be desirable. Corrosion and fouling, especially in the front end of the refinery, are of increasing concern. As the nature of the crude you are processing changes, you encounter bottlenecks as you approach operating limits of certain process units. Crude switches also require additional lab analysis and analyzer maintenance, as do the increased specifications for the products. Off-spec product blends require rework or giveaway with very high associated costs. And finally, tying all this together, you have production plans to meet, and any slowdowns, process upsets, or inventory constraints can force us to diverge from these plans. So if we look at a view of the margin impact as we travel through the refinery, we see that there is a significant opportunity to either increase or decrease margins both at the front end with crude blending and at the rear end with product blending, in addition to the expected increases during the distillation, conversion, and treating processes. In fact, poor blending, where products have to be downgraded, can actually decrease the component market value compared to the market value of the component after processing in the production unit. So we are going to be discussing the challenges associated with crude oil blending specifically for the next several slides. So I'd like to pause at this point and find out how you, the audience, is currently blending crude today. So please check the box that best describes the method you currently use for crude blending. So the first option is tank gauging. Do you rely only on tanks for blending, where you determine the amount of each crude type by the change in volume of the various crude tanks? The second option is ratio blending. Do you use a simple ratio blend using volumetric flow meters where the recipe is determined from planning and scheduling? The third option is where you use feedback control from a simple analysis of the blended crude, either gravity or viscosity. So you blend to either a gravity or viscosity specification. And then the next option is an inline blending system using more comprehensive analysis of the blended crude as feedback to the ratio blend system. And finally, if you're not blending different crudes together, you can choose the last option. Okay, so I see that most of you are blending using either ratio blending with using volumetric flow meters. So most people actually are doing some sort of blending of their crude oils using volumetric meters. So let's now look then at some of the problems that are associated with those methods. So the first problem has to do with the blended crude analysis. If there is no detailed or comprehensive analysis of the crude, this could lead to process upsets, slowdowns, and production losses. So as an example, if you're blending to an API gravity spec of 25, this might not be the best indicator of the loading for each of the process units. You may have a crude which has a lot of heavy components and a lot of really light components, but is slim in the middle of the distillate range, also called a dumbbell crude. The API gravity will also not necessarily correlate to sulfur or asphaltene content or total acid number. The second problem relates to ineffective use of tanks with traditional crude blending methods. Tank gauging as a method for blending can also be problematic. Often the level measurement itself is very accurate, but other variables, including imperfections in the uniformity of the tank, temperature gradients, can lead to inaccuracies. Another common problem is stratification in the tanks, where the material in the bottom of the tank and the top of the tank is quite different due to ineffective or non-existent tank mixing. It is also often the case that due to storage capacity limitations, you are simultaneously filling and draining from the same tank, making it impossible to accurately measure the volume. These tank utilization issues can lead to inventory scheduling and demurrage costs. And finally, there are problems utilizing traditional volumetric flow measurements for crude blending. The impact of changing properties of the crude on the flow accuracy is really significant, leading to inaccurate and suboptimal blends. If using mechanical meters such as PD or turbine meters, the associated maintenance costs to keep the meters accurate can also be large, as meter factors need to be adjusted anytime a significantly different crude component is utilized and needs to be metered. Okay, so let's take a look at the operational problems that can result when the blended crudes are not optimized. We already talked about the fact that we can have asset deterioration due to corrosivity or fouling, bottlenecks or slowdowns caused by process unit loading, and the associated safety issues. Some of the problems associated with processing opportunity crudes were expected, and some caught some of the refiners completely off guard. For example, there were locations in the crude tower that had never experienced corrosion issues, which are now seeing severe deterioration as we are processing these discounted opportunity crudes. Another issue that can be impacted by non-optimized blending is loss of production due to crude switches and the ability to have a smooth transition. It has been reported that the average refiner running multiple crude types loses 4.5% of production due to crude switches. So that's really significant. So the challenge then is, how do we process these opportunity crudes efficiently and safely? What we are showing in this slide is that as the crude gets lower in price, there is an increase in the cost of asset integrity caused by the operational problems that I just described. With the more expensive crudes, it is difficult to maintain profitability, so there's a sweet spot where you can maximize profitability without having significant operational issues. Precise blending becomes critical as you see that an increase of just 1% of crude, which could have a differential of $6 per barrel, would save you $5.25 million for a 250,000 barrel a day refinery. If you don't blend accurately, you have no idea what it's costing you. So what does optimal crude blending look like in order to be in the sweet spot? Starting at a very high level, optimal blending means you would be able to meet production plans. This involves minimizing the differences from production plan to actual by utilizing the expected plan for amount of opportunity crude. You can also minimize the effects of crude switches by blending to the boiling point curve and maintaining the optimal loading of the process units. The second cornerstone of optimal blending is improved profitability by maximizing the use of opportunity crudes and maximizing asset life by avoiding corrosion and fouling issues. And thirdly, you want to meet changing market dynamics with flexible operations, allowing us to take advantage of a wider range of opportunity crudes and achieving flexible and nimble operations to adapt to a changing market conditions. We'll talk about the solutions we have to help you to achieve this optimal blending later in the webinar. But at this point, what we want to do is find out what you guys on the phone in this webinar are, how you are blending fuels now. So we're going to switch gears a little to talk about fuel blending. So we're really primarily talking about gasoline or diesel blending at this point. Although the blending solutions are similar, the challenges are quite different. So we want to take a moment to understand how you're blending your fuels. The first choice is using tank gauging on each of the components, sequentially filling the product blending tank and then testing it for properties in the laboratory. The second choice is using an inline blending system using flow meters to meet certain specifications, but you're blending again to a holding tank where the properties will be tested in the laboratory. And then the next two choices both involve inline blending systems with online analyzers, but in the first case, you are still blending to a holding tank, and in the next choice, you are blending directly to a pipeline or other shipment method with inline blend certification where there is no opportunity to doctor the blend. So please mark the choice that best fits the way that you blend. Okay, so it looks like most of you use a simple ratio blend system to a holding tank to meet certain specifications. And I think that is, from all the refiners that I've talked to, that is definitely the most common way that we are doing. Most of us do go to a holding tank and then then we use laboratory measurements to monitor the quality of the blend. So, given that, let's look now at what problems are associated with some of the traditional fuel blending methods. So, and especially for those that where there's a desire to improve the system. First, the blend system may have poor accuracy due to the use of traditional volumetric flow measurement or tank gauging methods. These legacy instruments and systems normally require significantly more maintenance and have higher process variability than the state-of-the-art technologies. Because of these issues, the regulatory blend control program doesn't give you the results you desire in terms of meeting product specifications consistently. One of the biggest problems that's identified for us is with the analyzers used on the product blends. For fuel blending, many, if not most refiners, have tried using some sort of an analyzer, most commonly some type of an NIR analyzer, to look at one or more properties to get real-time information during the blending operation. But many have had problems with the reliability of the analyzer, and some, or even many, have stopped using them completely and have gone back to doing the analysis in the laboratory. The chemometric models used to interpret the NIR spectrum is problematic in several ways. It requires 3 to 6 months of accurate lab samples just to develop the model. And then it is costly to maintain these predictive models for each blend component and product. The blend components are affected by changes in the operation of the refinery, and the models aren't flexible enough in their property predictions to respond to these changes. So the challenge for fuel blending is to meet all the tight product specifications, but not to exceed the specifications, because that reduces profitability. The key to meeting but not exceeding specifications is to decrease the variability in your blend. The graph represents this concept where if you have a wide variability, your target has to be significantly over the specification to make sure you always meet it, which is shown by the light blue in the current state. As you reduce your variability, you can move closer and closer to that target represented by the green line. And then your profit gain is then represented by the difference in cost between those two targets. So, analogous to what we talked about for crude blending, let's look at what optimal fuel blending looks like. We again want to meet production plans by producing the targeted amount of each product by avoiding downgrades. So, for example, 89 octane to 87. We want to maintain on-spec blending during the entire batch. Optimal blending also involves improved profitability by reducing inventory, minimizing giveaway, and utilizing the least costly components for the blend. We also want to meet the changing market demands associated with a changing crude slate and its impact on the component properties. Because clean fuel regulations are continually changing and being implemented throughout the globe, our blending systems have to be nimble and flexible to stay effective. We'll talk about the solutions we have to help you achieve this optimal blending in a few minutes. So before I discuss those details of Emerson's blending solution, I want to provide information about typical economic benefits that we have seen. Our solutions have been field proven at more than 90 refineries with typical ongoing savings. So what this chart shows are typical savings as a result of being able to reduce octane giveaway, vapor pressure giveaway, inventory reduction. I also showed tank rationalization, component optimization, and the elimination of marine demurrage costs. So these savings, of course, depend on your starting point, but are quite typical in the industry of what we've encountered. Okay, so now that we talked about what optimal blending looks like, let's look at what our systems are like. So we will begin talking about the Emerson solutions. So this triangle is meant to introduce the major components for our blending systems, and we will discuss each section separately. So the solution is similar whether we are talking about crude blending or fuels blending. So that's why we are discussing the solutions together. Emerson is now the one-stop shop for both process design expertise and execution. We not only specify the equipment and technology for optimal operation of your blender, but we design and build integrated systems that incorporate Emerson's best-in-class technologies and control. The key components for optimized blending involve high-accuracy measurement devices and high-performing control valves, which are at the foundation of building a high-performing blending system. These measurements and control devices are integrated into an inline blending system that is properly designed and sized to enable your throughput goals and control component ratios represented in the green section of the triangle. Another key component is an online analyzer, which is composed of sampling systems, analyzer shelters, and modeling. The analyzer is used to accurately and continuously assess component stream properties and blend properties for quality control. And the last component is the control system. The analyzer will feed property data into the control system to ensure proper blend adjustments are made in order to be on spec throughout the blend. The control system regulates the ratios of the flows of the components, verifies and automates the lineup needed to execute the blend, as well as interfaces with blend planning, scheduling, and logistics management systems. All four of these components work together to deliver optimized blending. With Emerson's breadth of solutions and depth of expertise, all your application needs can be met in one place. So we're going to talk about the details of that triangle now, and we'll start at the bottom of the triangle, which is the measurements, and more specifically the flow measurements, as this is really one of the very critical parts of the blender. The traditional flow meters that are used for fuel blending are turbine meters, where performance is affected by the fluid properties and the process conditions. This is shown by the chart depicting the shift in meter factor with a shift in the viscosity of the fluid. The meters are also susceptible to wear and damage, leading to decreases in performance. For crude blending, where there are flow meters used, many of them are simple uncompensated DP orifice technology, where there is again significant effect when fluid properties change, which is very common with the changing crude slates that we run today. The technology which is most commonly chosen today for optimal performance is the micromotion Coriolis meter. The benefits in using this meter for both crude and fuel blending is that they are extremely accurate, have no moving parts, and are independent of changes in the fluid properties. They're also multivariable and now have increased tolerance to two-phase flow, which is important for such fluids as butane and gasoline blending. They also feature an important diagnostic tool called Smart Meter Verification that allows the user to simply and easily verify the accuracy of the meter. So there is no guesswork. You know that the meters are giving you the performance you need. Coriolis meters can now accommodate very large flow rates, but we still encounter cases where ultrasonic meters are a better choice, especially in crude oil blending. The choice in flow metering will be optimized based on the customer needs. So we talked about the metering portion of the blending system, and now I'm going to turn the webinar over to my colleague Arnie Josephson to talk about the other important components to our overall solution, starting with our skid-mounted solution. Arnie?
Thanks, Julie. And I also would like to extend my welcome to the group that's on the webinar. Emerson's skid-mounted inline blending skids are delivered to the site pre-tested and ready to be tied into your existing piping. This means these blenders can be installed generally minimizing downtime. So the benefits of this system are available without consideration of a long plant outage or a turnaround schedule. You'll be able to proportionally introduce blend components simultaneously and continuously to a discharge header with an inline mixer. Thus, this delivers a homogeneous and on-spec product ready for direct shipment via rail, pipeline, or container. Inline blending facilitates a faster production rate and enables you to get the right blend correctly the first time. Among the benefits to the plant's operation is the ability to more efficiently use the finished product tankage, because waiting for adjustments is eliminated. Therefore, tank utilization rates increase, helping what is often a plant bottleneck, tank availability. Once you have proper measurement instruments and have integrated them into an inline blender designed for your particular process, the next equally important contributor to an integrated blending system is the analytical components. Online analysis of components and blended product or feedstock is known as a known contributor to plant profitability. As we have improved the performance of analyzers by moving from knock engines and gas chromatographs and other discrete analyzers to infrared spectrum analysis and chemometrical models, response and accuracy have generally improved. But maintenance of the chemometric models is both highly technical and mathematical at the same time. Many systems in this world of changing crude supplies are unable to cope with these changes in spectra and process, and it results in inaccurately measuring results that are outside of the model envelope. This leads to optimal blends, which reduce profitability by resulting in off-spec blends, both over and under. Emerson has partnered with Topnir, a supplier of a unique patented software solution for the problem. They capably analyze both the refinery crude feed and the finished products, thus providing a finished product blending solutions that offer better profitability at both ends of the refinery process. So like any other NIR, near-infrared analyzer, there is a light source in the infrared light region, a measurement cell with a defined path length, and a detector. The initial light signal is attenuated in the sample cell and read in the detector. The FTIR then performs a mathematical operation on the data to enrich the information as opposed to normal NIR. The difference comes in the methodology of prediction. Topnir technology uses a spectrum matching methodology as opposed to chemometric models to perform the prediction. Where chemometric models require months of laboratory data before a model development can even begin, Emerson's Topnir solution begins with only 20 samples for each grade of product. Then, standard reference spectrum with known analyses are used to densify the database, and known mixing rules are then applied. So the basic postulate of Emerson's Topnir solution is if the spectra are the same, the samples are the same. And if the samples are the same, then the properties are the same. One can see that not only is this Topnir model easier to develop, it is less subject to the changes that make chemometric models ineffective. So how does this work? The Topnir pattern recognition technology uses the nearest neighbors in the database to predict the properties of the new sample. This all occurs in less than 1 minute. And because of the densification of the database, prediction of samples outside the initial model construct can be accurately predicted. So the properties of reference samples that surround a new outlier sample are used to correctly predict that outlier's properties. This is something impossible in traditional chemometric models, where the model would need to be rebuilt in order to include the outliers. Why is this important? Because the utilization of opportunity crudes results in blends, both crude feeds and finished products, that have not been seen before. So while Topnir can accurately predict the results, chemometric models are ineffective. Another place where Topnir's methodology excels is in predicting additive response and enabling the accurate dosing of those additives. This includes octane response for an ethanol and MTBE for gasoline, and pour point, lubricity, coal filter plugging point, or cetane additives for diesel fuels. Emerson's measurement instrument, incorporated in the skid-mounted inline blending solution, when coupled with Topnir's advanced analysis tools, provides a complete technical solution to the blending needs both of the front end and the back end of the refinery. For crude blending, Topnir's characterization of total acid number and asphaltenes allows proper dosing of anti-corrosion additives and anti-fouling additives. This avoids excessive addition of additives, which are expensive, and still provides the necessary level of downstream protection, which significantly improves the operability and profitability of the plant. So, to summarize the differences between traditional NIR methods and Topnir solutions, it's easy to see that Topnir significantly reduces the effort and related costs of model development, improves system response, and simplifies model maintenance. Let's switch over to the top part of the pyramid, which is controls. Emerson's SmartProcess blend contains 8 standard modules, which include regulatory controls, route management, quality control, order management, offline optimization, online optimization, tank quality integration, analyzer interfaces, and order management. These modules interface to the refinery planning software, and through that to the MES ERP software in the refinery. This means that all the functions required to properly manage the blending operation within the refinery reside in Emerson's solution. Emerson Control Suite can interface and work through your refinery DCS, Emerson or not, so your previous automation solutions do not preclude using Emerson's solution. For crude blending, the Emerson SmartProcess blend coupled with Topnir's advanced analysis and prediction capabilities can be coupled with APC to provide feed-forward, feedback control of the downstream units. This helps minimize the disruptions to downstream units from any crude changes. We all know that refining optimization and planning is a very complex problem. Planning for gasoline, diesel, and jet orders requires purchasing the correct crude slate at the same time you're trying to buy at the lowest prices. So let's look at DeltaV's controls again. There are 4 basic modules involved in the direct control of the blend, each of which can be operated somewhat independently from the others. These modules include blend start and stop. The purpose of this module is to automate the blending system startup and shutdown. This module performs sequencing and ramping of the component valves until the proper flows are established and the flow ratio controller can take over. The second is the blend ratio control. This is a real-time application that performs a calculation of component flow and matches it against the targets to meet the total blend flow rate required. The third is blend property control, designed to use the analyzer feedback to trim the ratio targets such that the blended product meets the specified quality targets. These include RON and RVP as the major ones. And the fourth is blend optimization, an online application that requires calculation of instantaneous quality targets for the blend property controller, such that the final blended material always meets given set of specifications. Let's take a minute and look at Emerson services. Emerson offers 3 types of engineering studies: comprehensive studies, front-end engineering design studies, and detailed engineering studies. All studies are based on the industry's broadest and deepest range of expertise and are covered by available performance guarantees. These are designed to give manufacturers confidence that they're designed to meet accuracy, capacity, homogeneity, and contamination goals. During the feed phase, a performance guarantee will be specified for your process. The three pillars of performance guarantees are optimization, capacity, and quality. Emerson is your one-stop for both process design expertise and execution. With over 100 studies conducted globally, we have been the one trusted partner for clients like you. Project services. By initiating, planning, and executing all of your project deliverables, from scheduling and procurement to fabrication, factory acceptance testing, and commissioning, Emerson Blending Project Management and Execution Service can help you minimize risk, reduce complexity, lower cost, and simplify project execution. Working with Emerson, you can have a single point responsibility for your entire project. Well, what about after sales? What about when it's all over? Our global services and support are readily available to maintain your system and keep its performance up to top shape. Our offerings include commissioning, calibration services for instrumentation, training, spare parts management, field maintenance work, and long-term service agreements. With a variety of service centers and over 400 service engineers all over the world, we can service your needs locally and efficiently. So we said we'd show you some proven results. Let's take a look at 4 examples. In the first one, a U.S. refiner saved $1.5 million with more accurate crude blending system. A great example of how Emerson technology was used to significantly benefit the operations and profitability by improving the crude blending system. This refiner originally used uncompensated DP flow measurement to ratio the components for crude blend, and they found that changes in crude properties affected the accuracy of the measurement too significantly. After that, they switched to using tank level measurement. This too turned out to be problematic because they often needed to fill and empty the tank at the same time. Therefore, they couldn't control the precise ratio based on either of these methods. And on top of that, the crude storage tanks were often not becoming empty when they were scheduled to be empty. As a result, they had demurrage for the vessels that were waiting to deliver the components or the crudes to the refinery. What was the resolution? They installed 4 high-capacity elite Coriolis meters to more precisely control the blend ratios. This allowed the refiner to take advantage of the price differential between the various crude stocks and to decrease the demurrage cost because the tanks were becoming empty when they were supposed to become empty. The business results were significant just by taking advantage of crude differentials and reduced demurrage costs. These 2 things resulted in savings of $1.5 million in just 5 months. The operational benefits were more difficult to quantify, but just as important. This refiner makes most of their money by converting the heaviest fraction of the crude oil into saleable products. So always filling the vacuum tower and the coker was essential to profitability. Blending to a precise ratio allowed them to accomplish this. It also gave them improved flexibility for crude unit operation, leading to better cuts and improved optimization downstream. And finally, they can run closer to the unit constraints and have less allowance for error in planning. The last point involves the coker. If the blended crude has too many heavy ends, there is a possibility of producing undesirable shot coke. This can result in a safety issue when the shot coke is released from the coke drum. The second example is for a refiner that blends direct to pipeline. He needed his blends to be on spec immediately and continuously during the blend. His state regulators were regularly monitoring the blend quality to ensure that the blended product met specs. And they were about to lose their license to blend directly to the pipeline because of non-compliance with specifications. They identified the problem as the blending system was because of the turbine meters used to control the blend ratios, and they were not consistently giving them accurate measurements. This was due to the fact that they were mechanical meters with moving parts that wear over time. To maintain the meter's accuracy, they would need to take them out of service to replace bearings and other parts. The solution was that they replaced this turbine meters with micromotion Coriolis meters for all the components. They also added a meter on the back end of the blender for final custody transfer to the pipeline. Since there are no moving parts in the Coriolis meter, there are no parts to wear and no associated maintenance cost. The result was they were able to consistently meet their product quality specifications for the pipeline transfer of a product. They improved their uptime and decreased their maintenance cost. The balance between the components meters and the final blend meters improved by 3.5%, verifying the accuracy of the meters by the mass balance. The savings calculated by this customer are over $300,000 per year. In our third example, we did a full project for a Romanian refiner. We're showing you the savings of $14 million. One of our clients captured after the implementation of a modernized inline blending system. This customer was blending to tanks and had several inefficiencies due to touch-ups, poor tank utilization, non-optimized component usage, and an intensive laboratory analysis schedule. We conducted a feed to redesign their process from tank blending to modernized inline blending. We provided a turnkey inline blending system with integrated process controls, optimizer, NIR, online analyzer, and resulted in the savings of $14 million. This came from better tank utilization, reduced product giveaway, higher throughputs, and optimized component usage. And in the last example, we have a major European refinery that was again able to improve his operation. He was faced with clean fuels regulations and was still doing tank blending with the related problems in analysis, reblends, and property giveaway. This was complicated by a changing marketplace where different customers faced different environmental requirements. Everything was for export. Emerson started with a feed to define the opportunities to improve for improvement, provided inline blending with SmartProcess blend and optimization. This was based on NIR analysis that resulted in the ability to produce certified blends direct to tanker ships and also to pipeline. This also provided increased tank utilization and allowed them to rationalize their tank farm. The result, a 10% reduction in inventory compliance with environmental requirements, and $2 million in giveaway savings. This was all coupled with a greater dependability and higher availability. So, how do you get started? We can help you on your path to better performance and suggest you schedule a meeting with one of our subject matter experts. Our blending SMEs will work closely with you to understand your objectives and design requirements. From there, we'll collect the necessary inputs needed to properly design a process and solution. This will enable you to meet your objectives. The SME will then review all the inputs and design your process, specifying the equipment needed, and develop a project schedule, a budgetary estimate, and an estimate of the return on investment. Afterwards, the SME will deliver to you an all-encompassing design package. So now I'll turn it back over to Allison to see what kind of questions we've gotten from you guys.
Thank you so much, Arnie and Julie, for all this great information. As Arnie just mentioned, we're now going to open it up for questions. So as a reminder, you can use that Q&A chat panel to ask some questions. And it looks like, Julie, we've already got some, so I'll hand it over to you.
Okay, thanks, Allison. Yeah, so I see one of the questions that has just come up is regarding the flow meters. It says, what is the maximum flow capacity of a micromotion Coriolis meter with still getting a reasonable pressure drop? So that's a really good question, and is one I very commonly address whenever we talk to customers. And a single micromotion Coriolis meter now can measure upwards of 200,000 barrels a day through a single meter, and it depends on the properties of the fluid, but it's very typical to design a system where we have less than a half a psi pressure drop through the Coriolis meter, even at 200,000 barrels a day. So we can indeed measure very high flow rates now, pretty effectively, and still get a low pressure drop with Coriolis. Let's see. There are also quite some comments and some questions, which is very typical about the Topnir analyzer, which is certainly a huge differentiator for Emerson in the area of blending. And so there is a comment about advantages over a PLS-based modeling system, so partial least squares system. So Arnie, I think they possibly want us to further explain really the differences between the Topnir analyzer and a partial least squares based modeling techniques, and can you really effectively predict outliers?
Thank you, Julie. Yeah, this is a differentiator. We have done both types and have seen the pain of outliers for our clients, which is one of the things that brought us to the Topnir solution, because of a significant difference both in predictability and in model maintenance. Partial least squares relies on a mathematical integration of the area under the curve of the spectrum. And so you're not dealing with the spectrum natively like you do in Topnir. And if you remember the slide that we showed, if you have two samples that have the same fingerprint, we'll use the word spectrum and fingerprint interchangeably, then those samples have the same properties, because the IR spectrum shows all the components that are in that each sample, and if they match, then they'll have the same properties. This is proven technology for over 20 years. It's just that other people can't do it because it's patented. So you'll get some different opinions from people who can't sell Topnir, and that Topnir is an Emerson business partner. I hope that answers your question.
Yes, that's great. Thanks, Arnie. I see another question that's come in. I have a Honeywell DCS in my refinery, and how can this solution work with it? Arnie?
Well, Honeywell DCSs are fairly prevalent in the U.S., and that's something that we know. Emerson has developed a solution to work in conjunction with the Honeywell DCS and provide all the benefits of Emerson's DeltaV for the blender and communicate with the Honeywell DCS or anybody else's DCS. Information transfer in a refinery in a DCS system is something that is not proprietary. There have to be routes to transfer the data, and so that's what we're using. And in some cases, Emerson is going in and actually replacing somebody else's DCS in the whole refinery. So it's not a huge problem.
Okay, thank you. And I see another question. If you are blending using an analyzer and blending to a fluid property, how important are the flow measurement instruments, and what role do they play? There are two parts of this. The first, as we sort of discussed in the beginning, when you start a new blend and you want to follow a specific recipe during the start of the blend, that's one of the times when the blend flow controller is extremely important in order to meet specification. So it is used during, the accuracy of the meter during that time is absolutely critical. And especially if you're blending directly to a pipeline and for in-blend certification. But during the blend, it's also very important because the flow set point that is actually used during the entire point, even if you're adjusting your blend, it will have a flow set point, a certain rate that it's trying to meet. And so if your meter isn't accurate, then you're not going to meet that flow set point. So when you're trying to optimize your blends to meet that property specification, you need to know what the flow rate is so that you optimize your blend while meeting your quality specification at the same time. I hope that answers that question. And it looks like those are the main questions that we have at this point. So, Allison, I would turn it back over to you.
Well, thank you guys very much for answering all those questions. And if anybody on the webinar thinks of them any additional questions, don't hesitate to email us, and we can certainly respond quickly to those. And we want to thank you again for joining us on today's webinar. We will be sending out a link to this recording of the webinar tomorrow, along with all the additional resources that you can see on your right-hand side there. On behalf of our guests, Julie Valentine and Arnie Josephson, as well as everyone at Emerson, we thank you again for joining us and taking the time to view the webinar. We hope you have a great day. Thank you.